Hello everyone. Today we are going to be going through our assignment 1 questions from Dynamics 349. Today's featured study space is the Law Library breakout room where I am recording this video. So this is to prepare for the upcoming quiz, which is today. So this is my own study time, and I hope this video will help you when you are going back to study this on your own. So assignment 1 deals with rectilinear motion, which means it's a lot simpler. We're not dealing with any curvature, and our kinematics, like I said, are a lot simpler and easier to understand. So that is what we are going to be evaluated on today. So we have 5 problem sets, and let's get started with our first one. So in problem 1, we are observing a sandbag being dropped from a hot air balloon, which is ascending vertically at a constant speed of 6 meters per second. So this hint here, constant speed, means that we also have constant acceleration. And we see that this sandbag will hit the ground 8 seconds later. So we want to determine the speed of the bag as it hits the ground, speed of the bag, and the altitude that the balloon is at this instant. So there's 2 things that we need to keep in mind. So the first one is we have to first look at the motion of the bag. And we have to look at the motion of the balloon for the second part of the question. Now, since we pointed out that this does include constant acceleration, that means we get to use the constant acceleration equations. So if you look at your equation sheet, the first equation that we will be making use of is v is equal to v naught plus acceleration times time. And the second equation that we'll be using is x is equal to x naught plus v naught plus 0.5 at squared. Okay, so like I said, we have to evaluate the motion of the sandbag as well as the motion of the balloon. So if we were to draw this, we have our hot air balloon. And from the hot air balloon, we have a sandbag being thrown until it hits the ground. So we're going to start collecting our values that we need for this problem. So we are going to start with our motion of the balloon. So we're going to establish that this is positive. Oh, actually, we're only dealing with up and down motion. So let's just state that upwards is positive and downwards is negative. So since we are ascending at 6 meters per second, that means it is positive. So this is our constant speed, and this is going to be our VF for our balloon, and that means our V naught. We are assuming that our balloon is starting at 0 meters per second from the ground when it is motionless. And for our motion of the bag, we are going to say that our V naught is going to be 6 meters per second, right? Because it's traveling, until it's thrown off the balloon, it's traveling with the balloon as it moves upward. And let's see, anything else we are missing? We are going to put gravity is equal to negative 9.81, since we have its constant acceleration because gravity is the only acting force here, meters per second squared. And you'll notice that there's a negative here because gravity is acting downward, and we already said that that is going to be negative. So the first part of this, we are going to find our velocity of the bag as it hits the ground. So that is going to be this v here. So we're going to use this equation, v equals v naught plus a t. Oh yeah, and we also have the value of t. Let me just write that down. It takes 8 seconds for that bag to travel. Let's mark that in yellow actually, because that is the movement of the sandbag. Okay. So when we plug in our values, we have 6 meters per second, and that's positive as it travels upward before it goes downward. And this is plus, and you're going to see why this negative is important. It's negative 9.81 meters per second squared, times 8 seconds. And this is going to give us a negative value of velocity, which will be equal to 72.48 meters per second. And there's two ways you can answer this. As you can see in the answer key, it doesn't have a negative in front of it, but instead specifies a direction with a downward arrow. So you can answer like this, as long as you stated that the downwards direction was negative, or you can answer with the direction. You can answer 72.48 meters per second downwards, right? Because the bag is traveling down. All right, so now for part B of this question, we want to find the altitude of the balloon in this instant, right? So how high does the balloon have to be in order for the sandbag to take 8 seconds to hit the ground? So we're going to be using this second equation here, and the values for our sandbag, oops, sorry, I forgot. So the values for our balloon that we wrote down earlier. All right, so the x represents our height, so that is the value that we are looking for. And we're going to assume that our balloon, its x naught, is 0 meters, right? Because we're assuming that our balloon starts from the ground, motionless, right? So that's why our v naught is 0 meters per second, and that's why our x naught is 0 meters. So we're going to put 0 meters in, plus, and our v naught we said was 0 meters per second. Our t was 8 seconds, doesn't matter because that's going to be 0. The only term that we're really paying attention to here is this last term. Right, so we have our gravity and our time. And so, using this equation, we get a value of 313.92 meters. And this is our answer for the altitude that our balloon is at. Right, so that is our first question. So our first question used constant acceleration. All right, but our second question is a little different. We have velocity given as a function of time. So this is just a little something new. Right, so because it's a function of time, it's not constant. So we're going to have to use some different principles to solve our values for this question. So we're given when t is equal to 1 second, the particle is located 10 meters to the left of the origin. So we need to specify that in our system, left is negative and right is positive. And we're given two initial values here. We're given, to use a different color. We're given when t is equal to 1 second, it's located 10 meters left of origin. We're given a time and a position that correlate to each other. So now we want to determine the acceleration at a specific time period and displacement within a certain bound. So automatically this should kind of set in that we need to differentiate, right? Because we have velocity and we want to find acceleration. And displacement, now that we have a bound, these are going to represent our bounds when we integrate, right? So basically, we have displacement and we differentiate, we get velocity. And differentiate again, we get acceleration. But if we want to go backwards, that means we have to integrate. So we're given velocity, so we're going to have to differentiate to find acceleration, and then go backwards and integrate to find displacement. So we're looking for two things: the acceleration at a specific time, and displacement within a certain time period. So we're going to start with our first one. We're going to find acceleration. And since we are looking for acceleration at a certain time, we can see that our equation already contains time inside the function. So we don't have to change it at all, and we're simply just going to keep it in terms of t. So we're going to take our velocity, and we know that it's equal to, we're going to take our acceleration. We know that is equal to the derivative of our velocity with respect to time. We're going to keep it with respect to time. So this is just simple differentiation. So 12's constant is going to go away, and that t is going to come down from the t squared, and that's going to give us negative 6t. Now all we need to do is plug in t is equal to 4. And this is going to give us an acceleration of negative 6. And we plug that in, that's 4. And acceleration is going to be negative 24 meters per second squared. So that's our first one. And that negative just means that it's decelerating in the direction that it's traveling. All right. So next we are going to integrate to find our displacement function. So displacement, we're already set yet again because we are finding from a bound of time. And we know that our function already contains time, so we don't have to change that at all. We don't have to change around our variables, which is good. However, something to note, the initial values are there because we need to find c. We need to find our constant once we integrate. So that means the first step that we need to do is we need to find a general solution. General integrated equation. And you'll see why this will come in handy. So that means we have to, in order to find our displacement, we are going to have to integrate our velocity with respect to time. It's the first step. So we're going to start with integrate. This is 12 minus 3t squared with respect to t. And as we keep going, this is going to give us 12t minus t cubed. And this is going to have some constant in there. So we need to find that constant because it's still going to be important to solve our equation. And this is when our initial values come into play. So when we plug in those initial values, we know that our displacement was going to be negative 10 meters, right? Because we established with our system up here that positive direction is considered to the right. And since we're starting from the left, that means we are going to have negative 10 meters. Then it's going to give us 12 minus t cubed plus c. And our value for t is 1. So now that we have those initial statements plugged in, this is 12 minus 1 plus c. And we move that over. This is going to give us c is equal to negative 21. And I'm just going to circle that for now so we don't forget it. So now we have our general problem. This is x is equal to, we have 12t minus t cubed minus 21 as our c. It's an intermediate step, but we're not done yet because we still have to integrate with certain bounds. So we need to integrate within a certain time period, which is given to us as 0 to 10 seconds. So now that's all we have to do. So now we're going to integrate with bounds. All right, so in that case, x is equal to, I'm going to put our velocity function in here. And now we are integrating from bound 0 to 10. So when that happens, that's going to give us 12t minus t cubed. And this is from t to 0. Oh, sorry. Hold on, give me a second. Sorry about that. And then that is going to give us x is equal to, so that is 12, and plug in 10, minus 10 cubed, and that's minus, all of that's just going to be 0. So x is equal to negative 880 meters. So this is only displacement, so this shows that we are 880 meters left of origin in our displacement. So this is not including the distance traveled. Yeah, so that is the third part of our question. So we want to find the distance that the particle travels as well. So we have our displacement, but now we need our distance. So let me just move these around a bit. So we're going to use this equation here. So my apologies, I said that we needed this for our part B, when in fact we actually need this for our distance, not displacement. But we still have it anyways, and we're still going to make use of it. So let's grab some more space. So that's our first part of the question over there. All right, and now we're going to do part C. So let me just write this integrated equation that we found earlier, just so we can have it there. Okay. So for our final question, we are looking for distance traveled. All right, so to start off this question, we already found our general integrated equation, right? Especially for our value c, since this is going to be a little different. So distance traveled, when we want to consider the motion of a particle, since we are given it as a function, we start to notice that it may change direction over certain time intervals. And we want to account for that. So we're going to notice that our change in direction, right, so say this turning point here, is going to have a velocity of 0. Sorry, velocity equal to 0, like that. So because of this principle, we are looking for critical points in velocity. That's going to mark when we see changes. So to account for those critical points in velocity, we need to set velocity equal to 0. And we have to find time interval that the velocity equals 0 exists in. So because of that, we are going to start with our velocity. We're going to look for our critical values. Okay, so we have velocity is equal to 12 minus 3t squared. And we know that our endpoints, which are already set for us, are t equals to 0 and t equals to 10. So these count as our critical values as well. So we're just looking for a couple more. So we're going to set this equal to 0. It's going to give us 12 minus 3t squared. Let's move that 3t squared over. And we divide. So that's going to give us t squared equals 4. So that means t is equal to plus or negative 2. But we can't have negative time because we can't time travel. So we're just only going to use t is equal to 2. We're going to start with that. So now that we have our critical values, we're going to plug critical values of time into our position function. So that means we want our position at 0, which is our first bound, position at 2, which we just found, and position at 10, which is our end bound. So this is going to be 12, 0 minus, right, this is the equation from above, minus 0 cubed minus 21. 12 times 2, 2 cubed, minus 21, and this is 12 by 10, minus 10 cubed, minus 21. Okay, and next we are going to find what those give us. So the values that we find are equal to, we have negative 21, negative 5, and negative 901. So now what we're going to do, we're going to find the distance between each of these points, and then we are going to add them up. So negative 21 minus negative 15 has 16 difference, and this has a difference of 896 between 901 and 5. So when we add these together, that is going to give us 912 meters, and that is our answer for our distance traveled. So to recap, we have to find our initial equation for displacement. We have to use our initial values to find this constant 21 here. We have to find our turning points for our velocity by setting velocity equal to 0 and finding our critical values for time. And using those critical values, we plug those into our equation for position. Once we got those answers, we found the difference between each of the points and added them together as a sum. So that is question 2. Okay, so something a little different now. For question 3, also a problem that doesn't have constant acceleration, where velocity is given as a function of position, of x. And it wants us to transform to find velocity and acceleration as functions of time. And again, we have these initial values that we have to work with as well. So because it's not constant acceleration, we can't use those equations that we used from the first question. We have to do something a little different. So, like we said, we need to transform velocity into a function of time. So how are we going to do that? Because we are given x in this equation. Well, there are some equations that we can make use of from our equation sheet. So velocity, as a standard, we know is equal to dx over dt. So we're going to use this to help solve our equation. So first things first, we are going to use this equation. So, sorry, let me write, this is for part A. And we're going to use our velocity. And this form works because we have the dt that we're looking for, and we have the dx, which is already included. I'm looking for. So we're going to rewrite velocity as dx over dt. So if we start with that, on the left side, then have our equation on the right side. We want to move over our dx to be with dt. Sorry, dx to be with our x's and our dt to stand on its own. So when we do that, we are going to have dt is going to be on its own, and this is going to equal 1 over negative 4x squared dx. Okay, so the next part, we are going to integrate both of these sides so we can get t on its own. So let me just write the steps that we did as well. Move dx with x's, and this is integrate. Okay, so we are integrating with the bounds. This is where our initial statement comes in. This is with respect to t. So t is going to be from 0 to t. And this is going to be from, value 2 to x. Okay, so once we integrate, that is going to give us t is equal to, we're going to kick out this negative 1 over 4. We have integral of 1 over x squared dx from 2 to x. Sorry, let me put this in here. It's from 0 to t. It's just going to be t. And continuing to integrate this, we have negative 1 over 4, and this is negative 1 over x from 2 to x. Okay, and we don't need a plus c because we have these bounds. So now we want to isolate x. So let's continue solving this. This is t, this is negative 1 over 4, and this is going to give us negative 1 over 2. Oops. 1 over 2 minus, well, I guess plus in this case, 1 over x. T is equal to 8 minus 1 over 4x. And we want to isolate for x. So I'm going to skip a couple steps, but this is going to give us x is equal to 2 over 8t plus 1. All right, so actually I am going to go through how to get there, just for my sake. Okay, so let's get rid of the 8 by multiplying both sides by 8. So that's going to give us 8t equals, that's just going to be 1 now, minus 8 over 4x, which we can rewrite as 2x. Two over x. Okay, and if we flip, so let's move this over, so 18 minus 1 equals negative 2 over x. If we flip things around, this is going to give us 1 over 8t minus 1 equals x over 2, negative x over 2. And if we cross multiply and divide, that is going to give us 2, 8t minus 1, negative, equals x. All right. Sorry, I think I may have done something wrong here, because in actuality, it's supposed to be positive. Yes, so I'm going to leave that up to you guys to check my work. But anyways, now we have x in terms of t. And so you're probably thinking, what's next? So what we can do, we can plug this x as a function of t into our original velocity equation. So when that happens, so we're going to bring it up here, because I ran out of room. Let's just draw an arrow. We said x was equal to 2 over 8t plus 1. So we're going to take this function here, in this part of our question, and we're going to plug in x. So when that happens, it's going to give us v, so negative 4. Inside the brackets, we have 2, 8t plus 1 squared. as it sits in place for our x, so that's going to give us v is negative 4. Inside our brackets we have 4, and then that's 8t plus 1 squared. And finally, that is going to give us v is equal to negative 16 over 8t plus 1 squared. And that is the answer to our first problem. So now our second problem wants us to work to find acceleration. So we're going to start this off by